Hello everyone and warm welcome to QuantPy. In this video, we are going to discuss the Dupire Local Volatility Model. A very similar approach was also developed by Derman and Carney, so the model also carries their name, but we shall refer to it by Dupire. This is for convenience only. The model is super simple. It modifies the Black Scholes assumption of constant volatility and assumes that the volatility is a function of time and the stock price. But the implications of this simple modification are profound. We shall cover several of these in this series so that we have a good understanding of what the local volatility model is and what it isn't. The aim is to understand the model and to understand it well, including how it fits into the wider hierarchy of models. We will start by explaining the problems with some of the Black Scholes assumptions and how the local volatility model fixes some of them. We will then derive the Dupire PDE, which is a partial differential equation in two variables. It contains partial derivatives of market prices of call options with respect to strike and maturity, and the local volatility function appears in this PDE as one of the coefficients. One can contrast this PDE against the Valuation PDE, which contains the derivatives of option price with respect to stock price and time, similar to the Black Scholes PDE we saw before. So the Dupire PDE is like the adjoint or dual of the Valuation PDE. We shall also highlight the connection with the Fokker Planck Equation, and towards the end of the video provide an alternative derivation of the Dupire PDE, which uses the Fokker Planck Equation and the option price formula. This is the approach that Dupire adopted in the original derivation, by the way. The LV PDE can also be expressed in terms of moneyness instead of strike, and also in terms of Black Scholes implied volatility instead of the call option price. But as the transformations are just mechanical steps with a couple of tricks, we shall cover their derivations in a separate video. But nevertheless, we show the results here for completeness and for the context. In the following video, we shall explain how the concept of local volatility model is linked with the stochastic volatility and with the implied volatility. This shall give us a good conceptual understanding of the local volatility model, and we shall then show in a subsequent video how to calibrate the model to the market prices. To motivate the need for modifications to the Black Scholes, let's quickly discuss some of the key assumptions that the Black Scholes made in order to obtain a nice pricing formula. You don't get nice formulae without making bold assumptions, right? They assume that the stock price follows a geometric Brownian motion, which implies that the log returns are normally distributed with the constant coefficients. So the instantaneous volatility is constant. Mathematically, it looks as follows. Now, when you look at the distribution of financial asset returns, you frequently find that the return distribution doesn't look Gaussian. It has higher peak and fatter tails compared to the normal distribution, meaning very small and very large returns are realized more often than a normal distribution would imply. Similarly, volatility of return changes over time and hence doesn't appear constant. Supply and demand for different options are also different, which magnifies the impact. You see the results of the violation of these assumptions in the market prices of options. When you plot the implied volatility is a function of strike maturity. So you get a volatility surface which is not flat as the Black Scholes assumption imply. The strike dimension of the surface for a given maturity is called the smile curve, while the maturity dimension is called the term structure of volatility. Now, when you see these anomalies, you will naturally want to revisit the Black Scholes assumptions and see which ones need changing. For example, you can say the diffusion assumption is not appropriate and add jumps to the stock price dynamics, or make the volatility stochastic, or make changes to several assumptions at the same time. So in this regard, what the local volatility model does is to make the volatility a function of time and the stock price. Note it is a deterministic function of t and s as opposed to a stochastic function. This simple specification can produce the current market prices of options, though the implied dynamics for future time are hopeless. For example, if the characteristic of the volatility surface are such that the smile curve is very steep for the shorter maturities and flattens as maturity increases, then surely one will conclude that the short end of the smile curve in, say, 5 years' time will be relatively flat because short-term maturity of the volatility surface in 5 years' time refers to the same time period as the today's 5-year maturity, which today data says is flat. But we know considerations behind the supply and demand for the December 2024 contract will be quite different when we get closer to that date, and it will most likely start behaving like today's short-term maturities. But local volatility only uses today prices and makes no assumptions about their behavior over time, and that's the main weakness of the model. It provides perfect fit to today's data, but when the data changes, the performance deteriorates and you will need to refit. Often, refitting leads to significant changes in the surface and hedge ratios and the prices of exotic options, which you won't like. You do remember our discussion of local. Essentially, volatility varies by the level of stock price. A function of T and S can take many functional forms. For example, the constant elasticity of variance model assumes the following functional form for the volatility as a function of S. Notice if you substitute 1 for beta, you get the Black Scholes dynamics, which is the log normal. If you substitute 1 divided by 2, you get the square root model of CIR, which is the non-central chi-square. And if you substitute 0, you get the Bashlia type model, which is the normal model. Now, if you want to have the inverse relationship between the stock price and the volatility, the so-called leverage effect, which you can easily relate to by recalling that the markets are more volatile when the prices are depressed, then beta has to be large negative, say -3 or -4 at least. Negative beta generates the inverse relationship. For example, setting beta equal to -1 will give us this relationship. So now as stock price increases, the volatility declines and vice versa. You can also try the displaced diffusion or shifted log normal, which is easy to relate to based on the previous example, and it's also easy to see that by adding a power term you can make these two models special cases of a general model. These are examples of parametric models. By the way, with limited number of parameters, these models won't provide a perfect fit to the data, as one would expect. Now, if you assume that you have the option prices, say call options for continuum of strikes and maturities, then you can use the prices to infer a function whose form is unspecified, but the function can be chosen to provide a perfect fit to the data. You can call this non-parametric approach, and this is what the Dupire local volatility model does. So you get an equation that gives the implied volatility at a given strike and maturity as a function of the derivatives of the option prices, as we shall see. We saw a very similar situation in the short rate models. Remember, we said the constant coefficients short rate models, say the Vasicek, which models the short rate as an Ornstein-Uhlenbeck process, will not match the current prices of zero coupons, and the Hull-White extension, by making the drift time dependent, enables the model to match the current term structure. So the drift is a function of the current instantaneous forward rates and its derivatives with respect to the maturity. The Dupire model does a similar thing to the volatility, but the volatility is made a function of both time and the stock price, which is because we are matching the volatility surface, which has maturity dimensions like the term structure, and smile dimension, where the volatility varies by strike. So you get derivatives with respect to maturity and with respect to strike on the right hand side. And needless to say, if you use this relationship to calculate the local volatilities and then use the calculated volatilities to price the options via PDE or Monte Carlo, you will reproduce the initial input prices, which we already know, so not much value there. But the advantage is now you can price other options whose prices are not quoted or whose prices are path dependent consistently with the prices of vanilla options that you use to calibrate the local volatility surface. Sounds exciting, so let's start with the derivation of this Dupire PDE. It's very similar to the Fokker Planck equation. To see how, let's recall that the Fokker Planck equation describes the dynamics of the transition density forward in time. We represented the probability density as a function of the value of the process and time. We should have actually written it more formally as conditional on the initial value of the process at time t0, but we suppressed the initial conditions. Now the call option price has a similar representation. It is a function of maturity and strike, and we can write it as conditional on the current value of the stock price at time t. Notice K in capital T replace X in T, and we write initial conditions as current time t. This is standard terminology in the options, as you would know, so we represent today as small t and the maturity as capital T. So K and capital T are the variables of interest here, which can look strange in the beginning, but it becomes second nature eventually. The Dupire PDE also looks very similar to the Fokker Planck equation. Of course, there are some differences, but we are interested in the similarities here. Let's bring back the Fokker Planck equation and its simpler form. We know that for the scaled Brownian motion, the Fokker Planck equation is just the diffusion equation, and if we isolate the sigma term on one side, we see it's very similar to the Dupire equation. So estimating the local volatility is like estimating the diffusion coefficient, assuming you know the density at two different times, or maybe the whole solution. This is the famous inverse problem. Intuitively, this ought to be possible. Remember, in the diffusion equation solution video, we interpreted the diffusion coefficient in terms of the distribution of particles over time. So if you have been given the distribution of particles at two different times, say at time t and at time t plus delta t, then it does seem possible that we should be able to determine the diffusion coefficient by using the finite difference approximation of the derivatives. There are some technicalities, not insurmountable by any means, but we shall defer the details to the calibration video. Now the Dupire PDE is very similar. Call options replace the P, and the diffusion term, which is the local volatility function, is a function of K and T. So given the call option prices, we can estimate the volatility values at different levels of strike and maturity points. The equation is slightly complicated because of the non-constant parameters and drift term, but conceptually it's the same thing. That's reassuring, so we expect the derivation of the Dupire PDE to be very similar to the derivation of the Fokker Planck equation. Let's recall the procedure we used to derive the Fokker Planck equation. We started with the SDE, which in the present case is given at the top. We then applied Ito's lemma to a function. In the present case, the function would be the option payoff. We then applied the expectation to get rid of the stochastic integral and replaced it with the probability density. We then used integration by parts, as the call option prices are integral of the option payoff with respect to the probability density. So instead of evaluating the integral via integration by parts, we will make use of the call option price and its derivatives. In a way, the market has performed the integration for us by giving us the call option prices. So the repeated use of integration by parts will be replaced by the repeated search for the price and derivatives of the call option. Just in case you like integration by parts approach, then you would be happy to know that we will also show an alternative derivation of the Dupire PDE, which uses the integration by parts. Now let's take the call option price payoff. It's the maximum of the stock price at maturity minus K and 0. The plus sign indicates that only the positive payoff counts. We have the option, not the obligation, so we can't lose. Now let's apply Ito's lemma to the payoff. So K is fixed, time, which is capital T, is increasing, and the stock price is changing as well because it is a stochastic process. By the way, the payoff function is not twice continuously differentiable because remember its derivative jumps from 0 to 1 at K, so we can't apply Ito's lemma. But luckily, there's Tanaka-Meyer formula, an implication of which is that we can use Ito's lemma for the absolute value function and hence for the maximum function. This might sound like an exceptional discovery, but it isn't. They're objects called generalized functions or distribution functions that are discontinuous, but you can pretend they're smooth. So many of the rules of calculus work for them. You can view these as an extension of the mathematical concept of function, just like rational numbers are an extension of the integers. Delta function belongs to this class. We know it is 0 everywhere except at 0, where it has a huge spike. So it's not even a function, but you can treat it as a smooth function, and most of the theorems of calculus work for this function. One way to view that would be that this function only appears in the intermediate steps of some derivations and not in the final solution, and it's usually wrapped in an integral, and we know it has nice properties when it is in the integrand. Less abstractly, we know that the delta function is a limit of a sequence of smooth functions. Remember, it's the initial conditions for the diffusion equation, and we know the diffusion solution is a smooth function. So if you're going backward in time, so you're starting with a smooth function and then you will end up with the delta function. And it won't be too surprising then if someone were to prove that what theorems work for the elements of the sequence work for the limit as well. And now the maximum function, as we shall verify shortly, is the integral of the delta function. So it is much smoother by comparison. So when you hear people say taking derivatives in the generalized or distribution sense, it usually means you can apply the calculus rules to a discontinuous function because it has a link to the class of generalized or distribution functions. So we can use our Ito's lemma, which is the first derivative times the ds plus half the second derivative times the ds squared. We know that s minus k is the ramp function. As a function of s, it is 0 below k and has a slope of 1 above k. So we can write its derivative as the indicator function, which returns 0 if s is less than k and 1 otherwise. And we applied the chain rule as well because we have a compound expression inside the function argument, that is s minus k. It's harmless here though because k is constant, so it boils down to 1. Now we calculate the second derivative, which is the derivative of the indicator function. The indicator function goes from 0 to 1 at k, so the derivative is infinity at k and 0 otherwise. And this is precisely the definition of the delta function, so we get, I didn't write the chain rule because it will produce 1 as before. Now we can substitute these derivatives into the Ito's lemma or Tanaka formula to get. We will be needing the derivatives of the ramp function with respect to k as well in the future, so let's quickly calculate these and we will then continue with the derivation. Now we take partial derivatives of the payoff function with respect to k, treating s as constant. Again, we get the indicator function because the function slope is 1 only if s is greater than k, so nothing has changed. The chain rule will now produce minus sign though, so we get. Now differentiating this result, we get, and we know the derivative of the indicator function is equal to the delta function, and another application of the chain rule will produce a minus sign. which cancel the previous minus sign, so we get. So the first derivative of the payoff function with respect to k is equal to the negative of the indicator function, and the second derivative with respect to k is equal to the delta function. We will recall these results later on when needed. Now let's get back to our derivation. Substituting for ds and ds squared, we get ds is the equation at the top, and ds squared is just the square of the coefficients of Brownian times dt. Remember, dw squared equals dt, and dw times dt equals 0. Now we can combine the dt terms to get. And if we take expectation of both sides, the dB term becomes 0, and we are left with just the dt term. Now we can shift dt to the left hand side, interchange expectation and the derivative to get. This is the dominated or bounded convergence theorem. By the way, in the textbook, you would see this theorem is about interchanging limits and integrals, but differential is like limit and the expectation is like integral. So this is how the theorem fits in. Also, the textbook definition of the theorem requires that to use the theorem, the derivative of the payoff function must exist, but here we know the derivative is not defined in x equal to k. But remember the earlier discussion about the generalized and distribution functions. So we are applying the theorem in the distribution sense. Also note the derivative is wrapped inside the expectation or integral with respect to the probability density, which we know has compact support. Now interchanging the expectation and the sum and taking the constants out of the expectation, we get. Now if you would like to benchmark our progress against the Fokker Planck derivation, we have reached the integration by parts stage, and as mentioned before, manipulation through integration by parts will be replaced by manipulation of call option prices. Let's try to express the first expression in terms of the call option price. We can write the payoff of a call option in terms of indicator function. So it gives s minus k when s is greater than k and 0 otherwise. You can write the payoff in many different forms as a maximum function with a plus sign or as an indicator function. We choose whichever form is convenient in a given situation. Here we use the indicator function because it lets us split the payoff into two components, where each of the component only counts when the indicator function returns 1, so both sides are indeed the same. Now we can rearrange to get the term we are after on one side. We now take expectation of both sides, so we get. Now remember the risk-neutral valuation formula. Price of the option is equal to the expected discounted value under the risk-neutral measure. Multiplying through by exponential of RT and swapping the positions of the expressions on both sides of the equality, we get. So our first expression is then the undiscounted value of the call option. Now the second expression has got the indicator or Heaviside function, which we know is the derivative of the payoff. So let's reproduce the risk-neutral valuation formula. Let's take derivative with respect to k. We can interchange the expectation and the derivative. The derivative of this function is bounded, but is not defined in s equal to k as we discussed before. But we can still use the dominated convergence theorem in the distribution sense to justify the interchange. And we know from our earlier discussion that the derivative of the call payoff with respect to k is equal to minus 1 times the indicator function, so we get. If we shift exponential of RT to the left hand side, we see we can replace the second expectation by minus 1 times the exponential of RT times derivative of the call option with respect to k. Now we multiply by R. That's the first expression sorted. Let's move to the second expression now. Firstly, note that the expression inside the expectation returns a non-zero value only when s equals k. So nothing will change if we replace s squared by k squared outside, but we will be able to take k out of the expectation because it is a constant. This is very much in the spirit of the sifting out property of the direct delta function. Please look it up on the Wikipedia. Now we can write the expectation of the product of sigma squared and delta function in terms of conditional expectation using the Bayes theorem. This is a slightly complicated looking version of basically the same conditional expectation formula. Substituting the conditional expectation times the term in the denominator in our equation, we get. So the first expression on the right hand side is the local volatility, as we shall explain shortly, and we need to find a way to express the second expression in terms of the option price. We saw earlier that the second derivative of the call option payoff with respect to the strike price is equal to the delta function. So we just take the call option price formula and take its second derivative with respect to k, where we interchange the derivative and the expectation. Now, making use of the earlier result, we substitute delta function for the derivative to get. So the expected value of this delta function, which by the way represents the probability of s equal to k, is equal to the undiscounted value of the second derivative of the call option with respect to k. We just need to multiply it by 1 divided by 2, so our running expression becomes. Now to simplify the result, let's take the risk-neutral valuation formula for call option and shift the exponential to the left-hand side. So this is now the undiscounted value of the call option. So the left-hand side is just the derivative of the undiscounted price with respect to t. And we can replace the exponential times c terms by the undiscounted price, so we get. Now we can isolate the conditional expectation of the sigma squared on the left hand side, and we get the Dupire PDE. By the way, we can write this conditional expectation as a function of k and t. To see that, we can write the conditional expectation as integral with respect to the conditional probability. So the sigma squared is integrated out, and we will have a function of k for each t. And we can write it alternatively as follows. So this is the local variance function. It gives the variance at time equal to t and stock price equal to k. And we can also relabel the parameters to define the function in terms of time and the stock price. And we can use this reparameterization to write the local volatility as a function of t and s. Essentially, to determine the volatility at time t when the stock price is s, we just feed these arguments to the function, and the function returns the local volatility. Now we see that the local volatility is the expectation of some random stochastic process, sigma, which suggests a connection with the stochastic volatility models. We shall explore this connection in more detail in a future video. For now, we just focus on the PDEs. Now we have the Dupire PDE in terms of the strike. As the strike by itself is not very meaningful, for example, strike of 10 for a stock worth 10 and a stock worth 1000 are very different things. So it's useful to write the Dupire PDE in terms of some scaled value, say the moneyness. So let's define a new variable y as equal to discounted value of the strike divided by the stock price. You can also interpret this as a strike scaled by the forward price of the same maturity as the option. Notice normally moneyness is defined the other way around, stock price divided by the strike, but given that we are talking about the current prices of options, which for a given maturity are displayed by strike, this form makes more sense because smile curve is usually shown as a function of strike, so having strike in the numerator allows for easy translation between the two representation. Remember, S0 as of today is a fixed number and it's the strike that differentiates the option prices. Now you can easily transform the derivative in terms of the new variable y. As the steps are mechanical, we will just write the results here and then detail the steps in a separate video. So this is how the Dupire PDE in terms of the moneyness looks like. You can also write the Dupire PDE in terms of Black Scholes implied volatility instead of the market prices of call options. To do so, we first set the undiscounted market price equal to the Black Scholes price. Remember, implied volatility is associated with the Black Scholes, so we need to bring the Black Scholes formula into the picture. As before, we have written the Black Scholes in terms of the parameters that matter to us here, and we have suppressed the other constants such as the stock price and the interest rate. Now the undiscounted Black Scholes is like the Black's formula, so we will use the Black's formula. We can transform the Black in terms of the moneyness variable. We also perform another change of variable, which is that we express the Black's formula in terms of total instantaneous variance, which we represent by W. Now we will need to transform the derivatives appearing in the Dupire PDE in terms of the derivatives of the Black's formula, and we get a complicated looking formula, which in fact is quite simple. It's easy to interpret if we isolate the local volatility on one side. So the numerator is just the derivative of total variance with respect to t. You know implied variance in a way represents the option price because the prices are quoted in terms of Black's implied volatility. So previously we had the partial derivative of the option price with respect to t, and now we have the derivative of the total variance with respect to t, so the numerator are very similar. The denominator looks more complicated now, but it's actually very similar to what we saw in the Dupire PDE. We have the derivative of variance with respect to y. Previously, we had the second derivative of option price with respect to k. So these are analogous to what we saw before. The y over w terms are just moneyness levels scaled by the variance, which again is quite intuitive. So if your option is deep in the money, but the variance is high, then you should be less confident that the option will stay in the money. And if your option is deep in the money and the variance is low, then you can start counting your chickens. You know they're going to hatch. Now let's quickly discuss connection with the valuation or pricing PDE and the Fokker Planck equation. We have the local volatility SDE. So using the delta hedging argument, we can derive the valuation PDE for an option like we did in the Black Scholes video. But let's try a different approach now. We can determine the change in the value of an option over an infinitesimal period using Ito's lemma. We substitute for ds and ds squared to get. We combine the dt terms. And now we know that the price of the option, which is the V, when scaled by the value of the bank account, will be a martingale under the risk-neutral measure, meaning its drift under the risk-neutral measure will be equal to R times V, and this is the valuation PDE derived. We can isolate the time derivative on the left-hand side to get. To determine the price V, we will need to solve this equation subject to the boundary conditions and terminal condition. which for call option is as follows. Now let's bring in the Dupire PDE. Notice this is in terms of the undiscounted option price, but that doesn't matter as discounting is trivial here. Now one solves this equation subject to the initial condition, and when you solve this equation you see you get current option price of all maturities in all strikes. So the Black Scholes Valuation PDE is a backward equation which gives the dynamics of the price of the option whose terminal payoff function is known. Dupire PDE is a forward PDE which, given the current stock price, gives the dynamics of the call options, or shall we say the call option surface. And if you want to push the analogy further, you can say that in the Dupire PDE, the strike is diffusing. So in the Black Scholes PDE, we treat K as a constant and S as a stochastic process. And the Dupire PDE, S0 is constant and K is diffusing. So you can view the Dupire PDE as the adjoint or dual of the Valuation PDE. Now we have already seen that the Dupire PDE is similar to the Fokker Planck or Kolmogorov forward equation. Remember, the derivation steps were very similar. We know the Fokker Planck describes the dynamics of the probability density, and the initial condition is given by delta. Because the starting value of the process is known, so the probability is concentrated at the current value, and this is what the delta function captures. You can see the parallels now. Actually, the Dupire original derivation was based on the Fokker Planck equation. As this approach is commonly adopted, let's go through the derivation quickly. It should give us additional insights into the connection between the Dupire PDE and the Fokker Planck equation. We know from the previous video that if a process is defined by generic SDE, then the Fokker Planck equation is as follows. For the local volatility SDE, the PDE becomes, we just rename the variables x to s and t to capital T and replace the drift and diffusion coefficients and took the constants out of the derivatives. Let's suppress the arguments to simplify the presentation. Now we can write the undiscounted price of a call option as expectation of the payoff. So we integrate the payoff with respect to the probability density. The lower integration limit is k because the option only pays if s is greater than k. Now we can take derivative with respect to t and interchange the derivative and the integral on the right hand side. Now we can substitute for the derivative of density from the Fokker Planck equation. Now integral of sum is equal to sum of integrals, so we get. Now we need to simplify the two expressions on the right hand side. We will start with the first expression. You will just use the integration by parts. We define the derivative term as dv and the remaining expression as u. Integrating dv removes the derivative and the differential of u is just equal to ds. We are treating k as a constant, by the way. Now we can substitute into the integration by parts to get. The first term is 0 at both ends. At the lower limit, when s equals k, we get 0, and the probability density of s going to infinity and a small interval is 0, so we get 0. Substituting into the main expression, we get. Let's move to the second expression now. We define the derivative term as dv and the remaining expression as u. Integrating dv, we get, and the differential of u is just equal to ds. Now we can substitute into the integration by parts to get. The first term is 0 at both ends. Integral on the right hand side removes the derivative, and the probability density of s going to infinity and a small interval is 0. Substituting into the main expression, we get. Now we need to write these in terms of the price of call options. So let's reproduce the call option price in terms of the probability density. Expanding the terms, we get. Now we can isolate the first object of interest on the left hand side and then substitute into the main expression. Now we have the probability density and the integral of the probability density on the right hand side, which we know are equal to the derivatives of the call option price with respect to k, as we can easily verify. Let's reproduce the call option price formula. Differentiating with respect to k, we get. This is the Leibniz rule, by the way. P and S don't depend on k, and the derivative of k is 1. So the integral of probability density is equal to the first derivative of the option price with respect to k. Differentiating again, we see that the probability density is equal to the second derivative with respect to k. Making these substitutions into the main expression, we get the Dupire PDE. We hope you enjoyed the video and look forward to seeing you in the next.